In last lecture, we talked about the temporal couple mode theory. Okay, this is a very important theory. I think this theory can be used for experimental research because it's very simple. Let me talk about this theory again. Okay. I think the most simple case is a filter. Okay, about this structure. This filter. The transmission at some frequency, we can go to 1. It's called Lorentz shift. We call Lorentz shift. Only 0. This. Transmission can be achieved. Okay. So this is a very important nature of this filter. So this is a physical picture. Okay. This is a waveguide. It's a 2D photonic control to a waveguide. This is an incoming wave, this outgoing wave. Okay. The outgoing wave can be decomposed to parts. Okay. This is has some physical meaning. Why I move my circle. So one part is just this is outgoing wave, and then direct reflect. Okay, they call it minus S1 plus. Okay, this -1 is due to the reciprocal principle. You can verify. It is minus. Another wave can go to a cavity. The cavity becomes resonant. They go to some circle. Okay, then they reflect it back. Put the two parts together. This is called outgoing wave. Okay. Outgoing wave has 2 parts. Then it has a transmission wave. The transmission wave only has only is due by the cavity affection. Due to influence of the cavity, this should be equal to 2 something. Okay. So this is a physical picture. So you can see that from this picture, it's possible that it is very possible this direct reflective wave, and this is maybe double reflective wave. This is reflective wave by the cavity because it can go into the cavity resonator, and then the wave can go around this cavity and leak it out. Okay, the 2 reflective wave can cancel it out. Okay, make this go to 0. Okay, no 0 reflection, and they achieve this 100% of the transmission. Okay, this is a physical explanation. So mathematical, this is the equation. Okay, this is a couple mode equation. Okay, it means the decay of the cavity amplitude. Okay, this is the oscillatory part. It's I omega A. It does not change the energy. It has 2 decay part. It coupled to the waveguide 1, the first part. The second part comes to waveguide 2. Okay, comes to waveguide 2. And this part is influence of the incoming wave to the cavity. Okay, the incoming wave is S1 plus. Okay, because S1 plus has an influence to this cavity. So this is the first equation. The second equation, okay. The outgoing wave has 2 parts. One is called direct reflection, okay, by the incoming wave that has a minus, okay, because it's a reflection wave. Another just influence of a cavity to this outgoing wave. Okay. So these 2 parts can be added together, get 0. They can constructively, they can destructively interference. Okay, direct reflection can be destructive interference of the reflection by the cavity, get 0. And this is transmission wave. The transmission wave is only caused by the cavity influence. Okay, it's by the cavity. Okay, this is just a very famous couple mode equation. Then you can use the Fourier transform to get a solution of the one equation, I just change the d over dt over I omega. Okay, I put others are the same. Then I get the A. Okay, so A can be represented by the S1 plus and put them together. Okay, how about definition of the transmission? Transmission just S2 minus over the S1 plus. So go here. Okay. Okay, this is called S2 minus, because S2 plus equal to 0. Okay, S2 minus over S1 plus. Okay, S2 minus is just 2 over tau A squared. Okay, this is due to the third equation. You can see. Okay, this is because this transmission wave is only determined by the cavity. So I just square it's 2 over tau 2 and A squared. Then all the incoming wave S1 plus. Okay, I put everything together. You can get this equation. It's easy to get. It's easy to get. From this equation, you can see that the T omega can be equal to 1, 1 T1 equal to T2, and omega equal to omega 0. Okay, they call it resonance frequency. And tau 1 equal to tau 2, it means that they have symmetry. This is a very simple case. But it's very universal. Okay, something you found that has a 100% transmission or 100% absorption. Typically, the reflection can be go to 0. But the reflection can go to 0. This is just due to the destructive interference of the two reflection waves. One is direct reflection, another just coupled to cavity return back. Okay, cavity return back. So this is a very important physical insight. I'll give you some example how to achieve this. Okay, so what's the essential part of this couple mode theory? They use channel. They see everything on the channel. Okay, they have a cavity. Okay, maybe they have many channels connect with cavity. They can be waveguide channel. Okay, with the lifetime tau 1. Okay, they can be coupled to free space. Free space also can be see a channel. They have lifetime tau 2. The cavity maybe has some lossy material. The lossy material also decay this amplitude of A in the cavity. They call it lossy channel, tau 3. Okay, they have many channels. Maybe they have 2 waveguide. They have coupled to the different channels. Okay, these channels are balanced with each other. Okay, so how to with the channel view? Okay, you will notice well. You can very useful for your research. Okay. First thing we consider tau 3 go to infinity. I mean there's no lossy channel. Okay, no lossy channel on tau 3. It means lifetime for this lossy channel go to infinity and no loss. It means the loss is no loss. Okay, when tau 1 equal to tau 2, they can achieve 100% radiation. Okay, similar to that. Okay, you can see there's a waveguide that goes with the cavity. The cavity resonance can couple to the free space. They can be 100%. Why? They have no reflection, as I said. There is some direction reflection. Another reflection goes to the cavity. Cavity goes to back. The two reflection contrast with interference. It cancels out. So every 100% radiation. Okay. This is the 100 radiation boundary condition. 100 radiation condition. Okay. Similarly, why is this important? Okay, you can see if why tau 1 should be equal to tau 2. If tau 1 is very large, okay, I say tau 1 is go to infinity, so lifetime is very long, so they cannot couple to waveguide mode. Okay, that means why is it important? Okay, I give a two limit case. When lifetime is long, you cannot couple to waveguide mode. What's the meaning with that? Sorry, not waveguide, cavity mode. They cannot couple to the cavity mode. Okay. When tau 1 goes to infinity, this is tau 1. Okay. This is tau 2. Okay. When tau 1 goes to infinity, that means this cavity. Because reciprocal theory, this cavity, if cavity is a TEC, I mean, there's a perfect electrical conductor. Okay, if there's source within the cavity, it does not leak it out. It does not couple to anything, right? That means the tall one goes to infinity. Okay. According to reciprocal theory, any wave goes to the PEC cavity, it totally reflect back, cannot go into its cavity, right? This is reciprocal theory. Okay, if a cavity is a perfect electric conductor, the source within the cavity cannot couple it out. Similarly, the wave cannot couple to its cavity. This is reciprocal theory. Okay, so this is a quality factor. That means quality factor also goes to infinity. This is the reason why visible Galilean mode cannot excite with a plane wave. Okay, if a visible Galilean mode, this is dielectric. Something to the later has a visible Galilean mode. Whispering Galilean mode. Okay. This is visible Galilean mode. It can be understood as total reflection. Total reflection. Okay. Total reflection. Something like this. Okay. It can be understood something like this. The field distribution is something like that. It has some. Okay. It's similar to the high order positive, negative, positive, negative, positive, negative. This is similar to octuple or something. This is called visible Galilean mode. Okay, that means dielectric. They have some visible Galilean mode with a very high quality factor. Okay, if you use plane wave, to excite visible Galilean mode, because the quality factor is very high. That means tau 1 is large. This is plane wave. Okay, it totally reflects it back. They cannot couple. Okay. They cannot couple because this quality factor is too high. Another understanding of why they cannot decide visible Galilean mode because the K is K vector, is E vector, E something like this. You can see here, along K direction, this is symmetry or E field, but this is an asymmetric field. It's asymmetric this field. Okay. So you can see that the asymmetry along this direction. Okay. That means along this direction, it's positive, negative, negative, positive, positive, negative, and asymmetric. Okay. Okay. Sorry. They cannot understand this. There's another reason. One reason is the Q factor is very high. Another is I cannot match all this E field because E field along this direction is symmetric. This is asymmetric. Okay. So this quality factor is too high. Okay. The way the reason people use a plane wave can excite the visible Galilean mode use leading because it has dipole emission in here. Okay. If it has gain material, it's quite different. Gain material. When wave go here, it has dipole emission because it has gain material. The emission dipole. So they can excite the visible Galilean mode. Okay, they can emit out. This is dipole source. This is the reason why they can excite. If no gain media, you use plane wave, you cannot excite the visible Galilean mode. Because visible Galilean mode has a very high Q factor. It's very similar to PEC. The wave can go here and go to return back. It cannot couple. Okay. This is a reason. Very difficult to excite. If no gain media, if you have a gain media, the gain media will emit. They can penetrate a little bit. They can penetrate, but this way, then they has a gain because it's a gain media. The gain media will have a dipole. They emit another light source. This can be excited with Galilean mode. Okay, this is difference because it's some nonlinear. It has some gain. It has gain media, has dipole source. That means they put some dipole source within this cavity. They might excite with Galilean. Okay, this is the first situation where the tau 1 goes to infinity. Okay, tau 1 goes to infinity, lifetime is too long, they cannot couple. Okay. Another situation, tau 1 too short. The tau 1 goes to 0. Okay, so wave. This is the wave is easy to couple here. It's easy to couple to waveguide. But they just go one wrong, they go out. Okay. They use to couple here when tau 1 goes to 0, but they move. The cavity is the coating factor is very low. Coating factor low, they can just go one circle, they can go out. Okay. If a coating is high, they can go many circles, the resonance many times, then they can go out. Okay. This is the reason. So when tau small, this it means that they just go few circle. Two with that means they has go few circle before radiation. Okay. So they have two situations. Okay. One situation that means the quality factor is very high. When quality factor is very high, you can understand it's a perfect electrical conductor. The wave cannot couple into its cat. It totally reflects back. If the quality factor is too small, they can couple to its cavity, but the cavity just go one wrong, it just emit out. Okay, the emission is very weak, radiation is very weak. Okay, the quality is too small. So this is the reason why you should choose this tau 1. It should equal to this and make this radiation. Cannot too small or cannot too large. Okay, this is the reason. Okay, this is a 100% radiation boundary condition. Another, I just draw this picture. It's a cavity. Okay, this is a plane wave. This is an absorption channel. Okay. This is a no waveguide channel. Okay, I call this is tau 1. So I just go back to the original form. This is called tau 2. This is called tau 3. I call this tau 2. This is tau 3. Okay, this is a very important application for this called 100% perfect absorber. How to achieve a perfect absorber? Perfect absorber. I mean it's 100% absorption. So the condition is very simple, just tau 2 equal to tau 3. Okay. They can achieve that. When they achieve that, this is absorption. But unfortunately, very narrow band at omega 0. It's a resonance frequency. Very narrow band. So I give the example by they call it 100% absorption. Why they can achieve 100% absorption? Okay, because I said when the plane wave goes to the cavity first they have direct reflection, they direct reflected. Another, they go into the cavity has a resonance, they go several circles, then go out. These two reflections can cancel it out, they come back to 100% absorption. Okay, I give an example by the Sha Wei professor in Stanford. He used this theory to understand how to increase the absorption of graphene. Everyone knows graphene is a very weak absorption. If it was one single sheet graphene, only absorbed maybe 100% weight, 100%, very small. It's transparent, they can do the electrode. So how they can do that? They do a grating, okay, with a hole. It has slab with a hole. Then they put DBR. So gives 1, gives 2, gives 1, gives 2. This is a DBR, okay? Distributed spread reflector. This is a grating with a hole. Okay. Just silicon with I can't remember. There's some this grating. This is some dielectric with holes. The dielectric with holes. Graphene just put. I put graphene to another color level. Put graphene above. Put the graphene above this. Okay, this is graphene above this grating. Okay, this graphene grating DBR. Okay, they use this structure to achieve the 100% absorption. The physical reason is very simple because it's guiding mode here. This is an incident wave, then go circle, then go around. They can cancel. It's direct reflection. They has DBR. There has another reflection. They cancel it out. Okay, it's direct reflection here. Then go to DBR reflection, cancel it out. They use this theory to understand why they can achieve the 100%. Why they can achieve the 100% absorption. Okay, they publish a paper. Okay, but this is narrow band. This is a quite narrow band. Only has a very narrow band. But it's application. When you do a photo detector. Why? When you make a graphene to a photo detector, this photo detector can be to a very narrow band. You can select some wavelengths. You can achieve 100% absorption. Right? This is good, but it's narrow band. Okay, if you can do a photo detector, it's a potential application. It's 100% absorption. Okay. Then why should you use DBR? They make a T go to 0. They make a T go to 0, right? T go to 0. This is first condition. Because 100% absorption. R should also go to 0, right? Reflection go to 0. Why reflection go to 0? Because there's two kinds of reflection. One direct reflection, another is go to resonant, and another direction. Okay, they cancel it out. Okay. You found that this is a very universal. When you learn a plasmonic, you found this a very deep reflection. Also something they cancel it out. It's a discrete interference. Because they have two different ways to reflection the wave. One is called direct reflection. They go to something direct. Then they have some cavity mode. They resonant, they go to reflect again and cancel it out. This is a reason. Okay. You can do a photo detector. But then when you do a solar cell, the situation is quite different. Everyone know this is K. This is active material. Typically, they have 400 nanometer to 800 nanometer. Okay. Maybe it's something like this. Okay. This is the material. Typically, material has a absorption, maybe broadband. Maybe broadband. You can use some to mix material. Okay. This is a broadband. How to increase absorption of solar cell? Because the increase absorption of solar cell, they can generate more electron hole pair. They can increase the performance of solar cell. This is active material. Okay, this is active material. This is active material. This is active material. Okay. So if I use this design, right? I make tau 2 equal to tau 3. What happened? If I make to tau 2 equal to tau 3, that has a very narrow band. Oh, maybe here. Okay, this is for the resonator. Okay, I use some resonator. Okay, increase the absorption of solar cell. Oh, this region is very good, but other region just go to 0. It's very bad, right? Because for solar cell, you should be a broadband absorption. How to do that? So typically they call it overcoupling regime. This is not good. Typically, tau 2 should be much larger than tau 3. I mean, the leaking loss, it should be much larger than the absorption loss. So they can pick a broadband. They can do to this condition. They call it an overcoupling regime. They call it overcoupling. This I call this critical coupling. So everyone should know this basic concept. What's the meaning of overcoupling? What's the meaning of critical coupling? So there's no free lunch, right? If you do the broadband, you cannot achieve 100%. You just maybe 20, 30, 20, you know, but it's broadband. You achieve 100%, it's narrowband, no free lunch. So this is a typical issue about this solar cell. Solar cells. So this is something I want to talk about this couple mode theory. I hope everyone can use this equation to fit your experimental results. You can fit your experimental results. Only has 3 unknown, omega 0, right? When you do something, you find some peak, it has a central frequency, you know omega 0 directly. It only has 2 unknowns, tau 1, tau 2. You can fit your experimental results with this. Very simple. Use a function f. I remember multi-level something f meaning max. This can be fit. It's multi-level function. So when you measure your results, okay, you get this spectrum, maybe transmission spectrum with the experimental results. First thing you can get an omega 0, right, with central frequency. Then you can fit your tau 1, tau 2 with this function, you can fit that. Then you can use this equation to explain your experimental results. This is useful. Okay. Because I know Fan, because Fan is a student of the House as a proposed couple mode theory. They published maybe 20 papers related to the couple mode theory. Okay, because they understand it very deeply, they can use this theory to solve a lot of problems. It's very powerful. Okay. This is a couple mode theory. So now I finish all the parts for photonic crystal. I finish all the parts because you have a. I remember you have a numerical. I just. Level is okay. Because I asked some staff, I don't know why. A bit too slow. No problem. Now I can go to the plasmonic part because I like to show some results for this numerical experiments. Okay. So I finished all the photonic crystal part. Then I can move to the plasmonics part. Go to the photonic plasma. I go to the plasmonic part. So why we should because plasmonic and photonic are just two main fields in this nanophotonic field. Okay, plasmonic is young. Okay, because people just study photonic first. Then started plasmonic. Okay, then started plasmonic. Plasmonic now still has some application in medical, in bioscience, in image. Okay, I mean in nonlinear optics, it still has many work. Okay, compared to photonic crystal. Because photonic crystal now, few paper. Okay, not too much. But plasmonic has many paper in this field. Why people study the photonics or plasmonics? You can see this is a very interesting picture, okay, about the purpose, okay. Everyone know that we study electronics, photonics, plasmonics. So what's the main purpose of electronics? Okay. Everyone know electronics can be made very small size. Why? Because the electron wavelength is very small, right? Like chip in computer, they can make very small, right? 10 nanometer, right? The channel very small. Okay. But the speed is slow. Why? They have LC delay. Inductance, capacitance, they have delay. Okay. So the speed is slow. Okay, it's up. Photonic speed can be high, okay, but the size is larger. Why? That is lambda over 2 limit. If I make the cavity, you should half wavelength or half dielectric wavelength. We cannot break this limit. Okay. This is a reason. We call diffraction limit or half limit. But how to achieve simultaneously high speed and a small size? plasmonics. This is the people who study this program. Okay. So I just list all the keywords for photonics and plasmonics. Right? For photonics, we study lossless media. Typically, we use silicon oxide. Okay, it's glass, lossless. We use silicon but at an infrared regime. Okay, everyone know the band gap was silicon maybe at a visible light regime, so we use infrared regime. This is almost lossless. Non-dispersive, because we talk about the inflow is constant, right? At a frequency of interest, we can assume that the permittivity is constant. We call it non-dispersive. Okay, this is photonics. It's simpler, okay, because it's constant. Another is large size, because hardware limit. You have no choice. You must do that. Okay. If you make a photonic band gap, you must use many layers, right? A, B, you repeat many times. For each layer, you cannot, it's left level 4. You cannot break this limit. This is proper. How to form the band gap? It's interference of a propagating wave. Remember there's some sphere, right? It's half length, have broad scattering. It's a reflected back, right? It's a propagating wave and interference. Constructively or destructively open up a band gap or band edge. It's a propagating wave. Okay. That typically can do the infrared. How about plasmonics? Quite different. Okay. Plasmonic lossy because of metal. Plasmonic typically they had happen in the visible light regime and for normal metal like silver and gold. It's a very lossy material. This is a big issue. We also have a big issue with plasmonics and the lossy. Okay. Another dispersive, very dispersive. That means different wavelengths they have different permittivity. Also a complex number. Because they have loss. But they can do very small size. They can achieve very small size. They can break the differential limit. Okay. Another thing, it's not interference of a propagating wave, but the interaction with surface. It's interference of a surface. This is a quite different field. So what's the meaning of plasmonics? Also, what's the meaning of this field? Everyone know who gave this name, plasmonics. I know this is by the Atwater, at Caltech. They give the name plasmonics. I think the different one has a different definition. Well, this is my definition. Okay. One EM wave to interact with the metallic nanostructures, they couple to a free electron near the metal surface. Okay. That means metal. How about the metal? There's many free electrons move around, okay, in the cavity. When the electron wave to illuminate this metal nanostructure, they can couple to the electron around its surface. They cannot couple to very deep because they decay very fast. They have very lossy material. Okay, so they couple to around the surface. Once they couple, they strongly interact. They have a complex linear, even nonlinear response. Okay. Because linear response, I give the omega, they reflect, they scatter wave also has a frequency of omega. If for nonlinear wave, I give the frequency omega, they can generate 2 omega or 3 omega. They call nonlinear optics, plasmonics. It's a very hot topic. I study this topic right now. Okay. They call it a linear, even nonlinear response. So this is coherence between photon and the collective electron. I mean, what's the mean collective electron? I mean they have electron move together, called collective electron. It's a generation polariton. Okay, this polariton is called a plasma. This is a quantum mechanics word. Photon and electron, they call a polariton. Okay. They pull them together called a polariton. Okay. This is them. This is them. They also called a plasma. But plasmonic is a field to study the interaction between EM and the metallic nanostructure. Okay, we call it photonic crystal is dielectric. We call it like a silicon oxide, aluminum oxide is dielectric, but the metallic is the silver, gold is the metallic structure. This is a field to study the interaction. This is a plasmonic. Okay. So the first thing, I think the first difficult thing is that how to derive the permittivity of this matter. How to derive the permittivity of the matter. Everyone should know this. To know it's a Joule model or a Lorentz model. Why? Oh, it's not the level. Too slow. Trouble? Why trouble? Because I asked the department to help today. I don't know why. No problem. Maybe next time I can show it to you. Okay. So let me talk about this plasmonics. For plasmonics, you know, theory is very difficult. Why? It's dispersive and lossy. Everything, I think, it's better to simulate all the plasmonic structure with commercial software because it's rigorous. When you do some model, like couple mode theory or some approximation model, I don't think this quite work for this structure because this is quite complicated. So for quite complicated structures, use commercial software to solve it. Like console, maybe luminol, numerical, and FDTD. What's okay? There's some maybe CST. You use 3 software to solve it. Okay. If you did not write code by yourself, I always write code by myself. Okay. So I did not use any commercial software, but maybe to do an experiment using commercial software. But for photonic crystal, I think you can write code by yourself because it's easy. Because it's a non-dispersive medium. It's very easy. I ask you to write a code for the numerical experiments. Right? If you realize this, you can almost solve all the photonic crystal problem. It's very simple. Okay. So it's not difficult. Now we talk about this Joule model, or is Joule model? Joule, a plasma model. Joule model, plasma model is a picture something like this. Okay, this is metal. This is ion. I mean it's nuclear. Okay, similar to nuclear. That's nuclear. It does not move because it's heavy. It's heavy, does not move. Electron freely. They move everywhere. They can move everywhere. It's electron. They call it free electron. They move everywhere. Okay. This is ion. So this does not move, it's steady. This is a physical picture about this plasma model or Joule model. It's very simple, okay, not difficult. It's a motion equation over electron, okay, over plasma field. They call plasma field because there's many electrons. Many electrons, they move very freely. They form a sea, like a sea. Okay, they move around, called plasma sea. Okay. Okay. This equation just Newton's law. Newton's law. Okay. Why you do this? M x dot just dx over dt. Okay. Very good. This acceleration. It's m gamma. Gamma is loss, some lossy term. X prime, okay, equal to E over E. Here E is just driven electromagnetic field. Okay. You can see that this is just ma, acceleration equal to force. Okay, this is just a lossy part, similar to friction force. Okay, it has some friction. Okay. This is Joule model. From this, use the Fourier transform. So x, this is because this I omega, this I is minus m omega square x plus m r I omega x equal to E over E. This is by the Fourier transform. Then you can get the x of difficult something m and full minus e is m minus omega square is minus omega square plus I omega gamma. Something like this. It's x. Okay. X, what's the meaning of x? X is just displacement, right? Similar displacement. This is the motion of the electron. It has a displacement. This displacement is caused by the driven force or electromagnetic field. Okay. So what's the definition of polarization? Polarization just see many electrons. Okay, just something like this. And just electron density. Okay, because this micro polarization, okay, it's a microscopic polarization. Okay, they have a collective electron behavior. So this N is electron density. Okay, the X just displacement. So pull that. Okay, so I get this P. This is a minus N. It's minus NE squared over M. What is go down. It's minus NE squared M. Slightly go here. Let me see what's the equation better. Okay. It's M. Why is no disappear? Touch. It's omega square. It's M omega square I gamma omega. Okay, this is a physical meaning. This is the mathematical equation or this polarization P. Okay, you know polarization, you can know the D. Right, it's electron flux is epsilon E plus P. Okay. Sorry, it has E something. This is a displacement. I just revealed this. Okay. I get a D field. So D just equals to epsilon 1 plus 1 minus N E. So it's omega P squared over omega squared plus I gamma omega E. Okay, here omega P we call the plasma frequency equal to N E squared epsilon 0 over M. This is a very important equation. The omega P we call a plasma frequency. Plasma frequency. Okay, finally we get this dielectric constant of permittivity equal to 1 minus omega P squared over omega squared plus I gamma omega. If lossless, 1 minus omega P squared over omega squared. This is lossless. It's lossless case. So from this equation, okay, first everyone should know this plasma frequency. Okay, it's NE squared over M epsilon 0. Another, if we ignore a loss, typically cannot ignore, but it has physical insight. How about this equation has physical insight? If omega go very small, if omega become very small, what happens? The epsilon become negative, right? The epsilon become negative. Okay. So at a long wavelength or low frequency, the permittivity of metal is negative. Okay. This is a very important and unique feature. Okay. We call a single negative material. If you have a higher, it's very high frequency, Emission equal to 1, right? Very high frequency. It means metal become transparent. Metal become transparent. Or low frequency, they're opaque. Okay. And high frequency, they're transparent. This is the basic nature of this metal material. See this metal. Then we can see this interesting result. Somewhere, when you do this model, you must fit your model with the experimental results, right? The red curve is the experimental result. The black is the theoretical result. Okay. First thing is that E voltage. Okay, people just draw E voltage in optical regime. Okay, this is the equation. 1 voltage is 1,240 over wavelengths in nanometer. Okay, so 1 E voltage equals to 100 to 1,240 nanometer. This subset it has a conversion relation. Okay. This E voltage is similar to h bar omega. You can see that at a low frequency, because it's E voltage, right? It's at a low frequency. Okay, they agree very well. Okay, agree very well. But at a higher frequency, especially in this region, you can see there has a very big difference about this model. Okay, this is a. But from this picture, we have two important things everyone should remember. The real part of permittivity of metal at a low frequency is negative. Okay, it's negative. If Emission is negative, this is a bulk. Okay, it's a half space. This is a free space. Let me draw this picture. Why negative is decay feature. Okay. If this is a plasma, it's a free, many free electrons. We call it plasma, the plasma C. This is EM wave. When the emission smaller than 0, what happens? When emission smaller than 0, mu equal to 1, no problem, right? Okay, so how about the K? K equal to K0, right? No problem. If emission smaller than 0, what happened? Complex, right? Pure imaginary. J, K0, no problem, right? I just go to a J, right? Because maybe -2 is just J, right? Complex number. If a K become complex number, EM wave will decay, right? Will decay, right? Because EM wave is E x P minus J K, we see around this, right? If J becomes decay, so the wave cannot penetrate. It just penetrates a little bit and decay. Okay. So this is a plasma. Okay. One is at a long wavelength. A long wavelength. This is a plasma. We have a break. 5 minutes break. Why this oscillator broke? There's a big difference here. First thing, everyone should remember, metal has negative permittivity. Even you see that it's very magic, but the emission is negative. I said when the emission is negative, we call it a bulk material. The EM wave cannot penetrate. It will decay very quickly. Because the K, when emission is negative, the K become imaginary. So that's a decay. They call it single negative material. This it naturally exists. Okay, it's real. Okay, we call double negative. This is not naturally exists. It's equivalent. But it is naturally exists. Another thing, at higher frequency regime here, the Joule model cannot agree with experimental results. Okay, so if you are a serious force, you establish a model, you fit the experiment result, you find some deviation. Then you can think about this. Which kind of feelings you are loose, you cannot capture. So this part is called interband transition. It's called interband transition. Okay. So the correct part, this is called intraband transition. So this Joule model only capture linear motion of electron. Force is linear, it cannot capture nonlinear. It's a linear motion. And the conduction band is intraband transition. So this Joule model capture intraband transition part very well, but it cannot capture interband transition part. Let me talk about intraband and interband, because it also connects with graphene plasmonics, so some emergent topic. This is an important semiconductor concept. What's the meaning of interband or intraband concept? Okay. So first thing, what's the fundamental difference between the insulator, semiconductor, and the metal? This is a very good picture. Everyone knows that for similar to photonic crystal. Okay, photonic crystal is just use couple mode theory, and the two pendulum they couple each other, they can split a band gap. Okay, every atom in an electronic system, every atom can be seen a oscillator, a harmonic oscillator. When this atom form a crystal lattice, they form a crystal some solid. This atom also interact with each other. They can split a band gap. Okay, this is called electronic band gap. It has a below the electronic band gap is a valence band. Okay, and above is called a conduction band. If the band gap is very large, this is called insulator. I mean, the electron should gain a lot. It's much energy. They can go jump to its conduction band. Okay, they call it insulator. Semiconductor like a silicon, maybe gallium, some semiconductor. The band gap is medium. Okay, not too large. So when you shine your light, the electron can be jumped to a conduction band. Then they can move, become a free electron. Then the remaining part is a hole, right? The general electron, it has a hole, okay? There's a Fermi level here. What's the meaning of Fermi level? Okay? Fermi level at 0 temperature, I mean the T goes to 0, okay? But at 0 K, I mean Kelvin temperature. At 0 temperature, below the Fermi level, all the bands are fully filled. Okay, this is the meaning of Fermi level. Okay. So why electron is so special? It's very different to photon. Okay. This is electron system. You put the electron to this system, the electron will occupy the one electronic state. Then you put another electron. This electron cannot occupy the same state of original electron. They must occupy another new state. Okay. They call it Pauli exclusion principle. It's different to photon. Okay. I draw this picture. What's the fundamental difference of electron and photon? For photon, okay, it's state 1, and it's state 2. That's many state. Okay. So plus 1 photon, okay, plus, they can occupy the state 1. Okay. I put another photon. They also have a probability occupy the state 1. They put a 3 photon, they also can occupy the state 1. Maybe they can occupy the other state. Okay. This is a photon. Okay. It has a probability to that. This is a photon. How about electrons? This state. This is the state 1, state 2, 4. Okay. The Pauli electron, it occupy state 1. Put another, no choice, state 2. Another, state 3, state 4. Okay. There's a Pauli exclusion principle. I mean, when the electron occupy this state, another electron must occupy another state. They cannot occupy the same state. They call it Pauli exclusion principle. It's a very fundamental thing. A photon, they can do that. Many photons can occupy the same thing. This is a fundamental difference. Okay. I go to back this Fermi C picture. Okay. This is Fermi C. Below is fully occupied. Okay. For how about the metal? The metal typically they have no band gap. That means conduction band and valence band are overlap. Okay, they overlap. So there's many free electrons. So I mean the electron give a very small energy, they can go about to the conduction band, they move freely. Okay, move freely. This is metal. So this is a basic picture. The very large band gap is insulator, and medium band gap is a semiconductor. No band gap is a metal. The overlap, no band. It's metal. So metal is a conduction band and valence bands are overlap. The conduction band and the valence band. The conduction band and valence band are overlap for metal. Okay, this is very important. Why is it metal? Why is it semiconductor? Okay. Because my course is nanophotonics, I cannot talk about too much about the semiconductor physics. But I know this very well. Okay. I know this very well. Okay. I have no time to talk about too much. What's the Fermi level? I don't know how to change the Fermi level. What's the meaning of Fermi level? If Fermi level is high, if material Fermi level is high, what's the meaning of that? Many electrons. Electron density is very high, right? If electron density is very high, because I said when you put an electron in this system, they occupy a state. Put another, they occupy the different state. They cannot occupy the same state due to the Pauli exclusion principle. So to increase the density of electron at Fermi level, just move about. No choice, move about. Okay. So how to increase the Fermi level? You just increase the electron density. How to increase the electron density? Doping, right? You can doping. Okay. You can doping. You can use light to shine, to illuminate the structure. They have generation electron hole here. They can increase the carrier. Okay. This is the basic concept. You can see what's the intraband and interband transition. Okay. Intraband transition is transition only at the conduction band or only at the valence band. For metal, only at the conduction band. Okay. You can see this electron can move here, move here. It just means the electron, this is a band structure. This is the band structure. It's similar to band structure in photonic crystal, but it's band structure for electron. This is K, this is omega. They call E, H bar omega is energy. Okay. This is the band structure. If the electron state only move at this conduction band, they call it intraband. Okay. But if the electron can move from the conduction band to valence band, or from valence band to conduction band, they call it interband transition. Okay. So just international, you know, so they can go a different band. Intra just only has one band. Okay. They call it intraband transition. This is a first thing. Okay. This is a very simple picture. But another intraband transition is a transition, first thing, between the conduction band, but what's the physical origin? It's an electron-electron interaction or electron screening effect. Okay, there's a many electron. Electron has interaction, very different to photon. Okay, why? Electron has charge. They have a Coulombic force, right? They have two positive electrons. They cannot go approach very near. They push them. It has Coulombic force. They have interaction. They call it electron-electron interaction. That interaction typically also coupled to some phonon. Okay, phonon. We call it acoustic wave. We couple them. This is part. This part is responsible for the plasmonic effect. This is responsible for the. Is mainly responsible for the imaginary part or complex conductivity. Okay. Imaginary part or because everything in metal will use conductivity, but use complex conductivity. If the complex conductivity is the imaginary part of complex conductivity is just real part over permittivity. Okay, the real part of permittivity, right? Sigma over I omega 0, right? So in sigma is complex over I omega 0 become a real, right? Become a real. So this is the part is responsible for plasmonic effect. So plasmonic effect is mainly due to the intraband transition part. Okay, mainly due to this part. Okay, so I go to the experimental result. You can see this part is very negative, right? It's a large negative value. It agreed very well. Why? because this part is responsible for plasmonic effect, because epsilon is negative. Okay. When I go to a higher frequency, you can see this is a lossy part. Lossy part has a very big deviation. Okay. So what's the meaning of lossy part? It's interband transition. Interband transition is just a transition between conduction and valence band. It's a generation electron hole pair. It's very important. It's a generation electron hole pair. Electron hole pair generation, also recombination. Okay, generation. Okay, this is the interband transition. And the mainly responsible for the rear part of conductivity. Right? What's the meaning of rear part of conductivity? Lossy. Right? Sigma E squared. According to the Poynting theorem, sigma E squared. If a sigma is rear, it's lossy part. Okay. So it is responsible for lossy part. If a sigma is pure imaginary, it's a real part. Okay. So interband transition is responsible for the lossy part. So this is the reason why you see a very big difference at the invariant part or lossy part. Okay. This is the reason. Okay. How to generate plasmonic effect? If intraband transition is dominant over interband transition, the plasmonic becomes significant. This is the key. Okay. If intraband dominates interband, the plasmonic effect becomes significant. Okay. Lossy cannot be too large. So we need to increase electron density or rising the Fermi level Why the metal like a silver gold has plasmonic effect at a visible light regime? Because the electron density is very high. Okay, the electron density is very high. Okay, so intraband transition or electron screening effect become very significant. Okay, other material also has a plasmonic effect, like gallium arsenide. Okay, consider nanowire. It's very nanowire, gallium arsenide. When you shine light, it generates many electrons. It also has a plasmonic effect, but this plasmonic effect only happens at terahertz. It cannot happen at the visible light. Why? It's just due to a Pauling principle. It's similar to graphene. I just draw this picture. So what's the physical origin of interband or intraband? Okay, this is a K, this is omega, this is a conduction band, this is valence band. Okay, if I Fermi level in here, this is a field. Okay, that means if I transition something go to here, they are forbidden, almost forbidden, right? Because it occupies. I said it's a Fermi level. This is a Fermi level. Before the Fermi level, the electrons are fully occupied due to the Pauling exclusion principle. Okay, no choice. So this transition are forbidden. Okay. This transition was meaning is interband transition are forbidden. So intraband will dominate, right? But if the go higher, this allowed it. Okay, this allowed it. So when you increase the Fermi level, what happens? I increase. I increase here. You must get a very high energy, right? The interband allow it. Okay. That means when you increase the Fermi level, you can have a short wavelength plasmonic effect exists. Okay. This is forbidden. This is forbidden. Okay. That means when I increase the Fermi level, you must have a very high energy. They have interband transition, right? So when you increase the Fermi level, I just increase the band for the plasmonic effect. Okay, if the Fermi level is very small, it has terahertz. Maybe in terahertz has a plasmonic effect. When I increase the Fermi level, I can go to a visible light. Okay, because I increase, this is forbidden. Okay, they can be visible light. Okay, this is the reason why we see graphene plasmonics. We see some 3,5 chemical. They also have plasmonic, but they're plasmonic at the middle infrared or terahertz because the Fermi level is not high enough. Okay, that means electron density is not high enough. In metal, electron density is very high, so Fermi level is very high. Okay, this is the reason. This is maybe this H bar omega, this H bar E1. I I just clarify carefully. This is very important. This is an emergent topic, a very hot topic because people study plasmonic in other materials. So it is carefully. Okay, I call this H bar omega 1. I call this H bar omega 2. I call this H bar omega 2. Okay. If Fermi level EF is small, H bar omega 2, this transition is allowed. This interband is allowed. So this is not good, right? And omega 2 larger than omega 1. Okay. That means at a higher frequency, if the interband is allowed, the plasmonic effect are suppressed, right? But at this situation, H bar omega 2 is forbidden. Because I increase the Fermi level, right? They have to fill, they cannot, right? They have no transition. Okay, so this is forbidden. So interband is forbidden. So this is allow the plasmonic effect, okay, at a higher frequency. Okay, they allow the plasmonic effect at a higher frequency. This is for the plasmonic. Okay. So for the lower Fermi level, if this H bar omega, there is no plasmonic, okay, because the Fermi level is low. Here, it has a plasmonic because interband transition is forbidden. So this is the reason why to do the graphene, people just add a very high voltage to right in the Fermi level. They make this kind of plasmonic, called graphene plasmonic. That's the thing. Like for the 3,5, some gallium arsenide material, people use light to illuminate, to generate many electrons. Okay, to make this kind of plasmonic. But even though this plasmonic has a tolerance, cannot have visible light, because the Fermi level cannot be so high compared to metal. This is, I just finished this part. This is semiconductor physics, very important. But how to capture interband transition by the mathematical model, interband transition? They just use Lorentz model. Okay, compared to Joule model, this is Joule model, right? Okay, acceleration, some friction force, okay, some lossy part. This is driven. They put another, okay. This is called a bond electron. It's similar to a spring and a ball. They have some restoring force, like spring and ball. They will return back, and they can capture the interband transition. Okay, you can see this. This is a key. You can just spring ball is a single key. Like also it back force and some bond electron. Okay, so finally we have how to represent the Imson. One part is one because it's initially okay. One part is the Joule model. We capture the intraband transition. Okay, this is mainly part for plasmonic effects. Okay, another just a Lorentz term. These are many terms typically. 3, 5. Okay, they can capture even and capture interband transition. Okay, they have the parameter should be fit to the experimental result. It's a Lorentz term. So this is a fully picture for this permittivity of the metal. You can use this model to do that. They have many, do some simulation in this model. It's interband and intraband transition. Okay, so I finished this interband and intraband transition. I know this Joule model and Lorentz model. Just draw this. It's better to draw this. This model is very famous. Plus sigma j. Aj over
omega j squared plus omega squared minus I gamma j. Here omega j, aj, and gamma j need to fit by experiment. This is the Joule part. This is the Lorentz part.
You can see that it's interesting why it has summation. Why it has summation? Because it mainly has a different transition interband. Okay. Intraband can be just one term. Okay. The electron-electron interaction part. It's an electron-electron interaction part. It's a generation electron hole here. Okay. It's interband transition. If you add them together, you can fit the experimental very well. That fits very well. Because the textbook does not teach this part, because this part is related to semiconductor physics. I teach this to you. I hope you can understand this. It's important. Okay. Because some students ask question, only metal, maybe silver, gold has a plasmonic effect. They ask this question to my supervisor. Okay. My supervisor also don't know. They ask me. Because I know this well, because it usually increase the Fermi level. Increase the Fermi level. This is an increase the density. This is the key. Okay. Now we talk about surface plasma. Surface plasma. A surface plasma. Okay. The picture is something is metal and dielectric. It's semi infinite two-layer medium. The semi-infinite two-layer medium is Emerson 1 and Emerson 2. It's X, it's Z. What's the meaning? What's the physical meaning of this surface plasma? Okay. So surface plasma, we also call it surface plasma polaton. Okay, polaton just meaning of electron coupled to photon. So Feynman gives a very interesting picture about a polaton. Okay, they said like a beer. Okay, everyone drinks a beer. Beer is a beer. We see the beer is an electron. Okay, it's a water. Or some water is an electron. Air is a photon. But it has a bubble, right? Around the electron and here, around the air and the beer, there has a bubble, right? Some bubble. This bubble is called polaton. They couple them. Okay. This is a intuitive picture. What's the meaning of polaton? Just the electron coupled to a photon. We call it polaton. Okay. Similar to water coupled to air, that has a bubble. Okay. This is an intuitive picture. They call it surface plasma polaton. And many names. Okay. People use this name. It's because it's from the physical. And if you learn the quantum optics, polaton is just entanglement state. This is another more advanced concept. This is a classical picture. This is because it's metal. This metal has a dispersive lossy media. It's described by the Joule Lorentz model. Okay, this is metal. When the electron inside this, when the electron interacts with this metal, because metal has many electrons. Okay, here they interact with that. They has a wave. They has eigenmode. Okay, this system has eigenmode. Very special eigenmode. This eigenmode propagating at an interface. Okay, they're propagating at an interface between the electron and the conductor. But they evanescently in the vertical direction. That means the field will decay along the dielectric, also decay along the metal. Okay, this is very special. I showed some movie. I draw a movie by myself. This is eigenmode. Okay, it's not excitation solution. You can say this is plasma. This is eigenmode. Okay. You can say first they propagate along this direction. When they decay, they have loss. Right? They propagate and decay. Okay, but along this direction, they also decay. Along this direction, also decay. They cannot. This is a physical picture. I draw this. You can see they propagation, also decay along this direction.
just stop. Every time I should touch something, I stop. Oh, I see. Okay. This is surface plasma. This is surface plasma. Oh, I remember every time I run this PPT, I should change something. I don't know why. Sensitivity. Oh, yeah. Duplicate. Every time. Let's see. Let's go. Okay. I go back this here. Okay. This is a surface plasma. I mean, they propagate along this direction, but they decay because it has losing material. The propagation constant is complex. So the propagation decay along this. Along the two direction, they decay. Okay. This is a decay profile. You can see along these two directions, they also decay. The decay speed along the metal is faster than the air. Okay. This is a physical picture. How to derive a dispersion relation? Okay, this is example. It's very simple, not difficult. First, you just assume it's TM wave or TE wave. Okay. Only TM wave can support the surface plasma. TE wave cannot support. What's the reason? For TE wave, the E field is along the y direction, right? Along the y direction. So N dot D, okay? So electrical flux also along the y direction. So N, I mean the normal vector on this interface dot D equal to 0 and no surface charge. No surface charge. They cannot support the surface plasma. Surface plasma only exists for TM wave. For TM wave, the H is along y direction, so I just assume this H in region 1 and region 2 with KX1, KZ1, K2, and KZ2. Okay, it's easy. And the boundary condition, I mean H field will continuous. This first equation, right? Another, just tangential E field along the X direction also continuous. Okay, so I just pull this two, pull this another continuous equation, and pull this equation together and consider this, consider this dispersion relationship for each layer. Kxy plus kzy is kx2 plus kz12 equal to minus 1 minus OC2. This is just k squared. I put them together to get this dispersion relation. Because I talked about this many, I think in here. Okay, because I talk about this, right, it's a two-layered media. First, you get this reflection coefficient for TM wave. Okay, you get this reflection coefficient. Then, you make this reflection coefficient go to infinity. You make this reflection coefficient go to infinity. It's a pole. It's a pole. Okay. I mean, reflection coefficient means the reflective wave over the incident wave, right? Reflective wave over incident wave. If no incident wave, no excitation, you still get reflection. This means eigen solution. Right? No excitation, the solution still exists. Okay. So it's a pole. You can say this is a reflection coefficient. The pole here, right? This pole go to 0. And make the pole go to 0 and do some simplification. Also can get this dispersion of surface mass. Okay. So it's easy to get. So I just jumped. Okay. It's same result from this. Okay. So the basic idea is just tangential continuous. H field and E field. You can get this dispersion relation. Okay. From this dispersion relation, it has a resonance condition. I just draw this carefully. This is a dispersion relation. It's very important. Okay, so Kx is tangential wave number. Okay, tangential wave number. Okay, this is x. Kx equal to omega over c epsilon 1 multiplied epsilon 2 over epsilon 1 plus epsilon 2. This is a very famous relation, very famous. Okay, it's something like this. Okay, so what happened? Epsilon 1 plus epsilon 2 go to 0. I mean, epsilon 1, I assume that is a glass. Okay. Glass typically epsilon is 2.25 glass. This is metal. I see this. Yeah, it's metal. If epsilon 2 equal to minus 2.5, I said they can be minus, right? I ignore loss. I mean, has small loss. I use I. Difference is I and be something 0.1. Okay. This is the typical value. Okay. I just ignore the small c. See what happened. If epsilon 1 plus epsilon 2 is about go to 0, what happened? What happened? Kx go to infinity. Right? Okay. The Kx goes to infinity. If Kx goes to infinity, how about Kz? Kx squared first thing plus Kz1 squared equal to K1 squared. Right? So Kz1 also go to I infinity, right? Imaginary part. Because of the real part, the Kx goes to infinity. The Kx goes to infinity. The K1 is just a real value for air region. For dielectric region, glass region. Okay. So Kz1 also goes to I infinity. I mean, it decay very fast. It decay very fast. Okay. Similarly, for metal also similar, but decay more faster. It's the Kx squared. When Kx squared goes to infinity, and plus Kz2 squared and the K2 squared. The Kz2 also goes to very fast, minus decay very fast. Because this is negative. Yeah, this is negative. Equal to K0 is negative. Decay much faster, okay, more faster than the air region. So you can see why it decay faster than the air, right? Metal decay faster than air. Okay. So this is the reason. Because the K2 is smaller than 0. K2 is smaller than 0. This is very large. Okay. So Kci squared equal to Ki squared minus Kx squared. Okay. So for metal, this is negative, this is more negative, so this is should be decay faster. Okay, so physical picture is something like this. One resonance, they decay very fast. Very fast. Okay. This is of 1. Okay. If we decay very fast, okay, then we can cut. When not necessary, this layer has a semi-infinity thickness. I can cut. This is D1, maybe this is D2. And D1 much smaller than lambda, and D2 much smaller than lambda, right? Because it decay very faster along this direction. No problem, I can cut. This is the reason why we can do the ultra small.
ultra small or ultra thin size for this still resonance. Okay, because it decay very fast. When kx go to there, go to infinity, this decay very fast along two direction. This is the first very important thing. We can do ultra small. Device cut signals. Another thing, remember dielectric waveguide. We need 3 layers, right? Insul 1, Insul 2, Insul 1. Insul 2 should be larger than Insul 1, right? It's a guided wave. And this thickness D around lambda over 2 or N, right? N2 around. Okay. So the most simple guiding structure for dielectric is 3 layers, right? Insul 1, Insul 2, Insul 1. Cannot be 2 layers. 2 layers cannot be guided. This is optical fiber, cladding layer, co-layer, but this is dielectric. And the thickness around half dielectric wavelengths. Okay, half dielectric wavelengths. And for plasmonic, it's dielectric guide. Plasmonic only has a 2 layer. Insul 1, Insul 2, right? They also can be guided way. They can be guided. Okay. Another thing, you can cut like this very thin. Like very thin. Cut. Cut. Like very thin. This D much smaller than the wavelength. Okay. They can break the half wavelength limit. They can break half wavelength limit. They can break half wavelength. So this is the reason why plasmonic is very interesting. It only can support this 2-layer medium. 2-layer medium. So this is the resonance condition. One achieved when the kx goes to infinity, they decay very fast vertical to interface. And decay along 2 directions. It's very unique. Okay, very unique. So this is so you can cut. Okay. This is a reason you can break. Another thing, however, this is an ideal case. I said I did not consider a lossy part. Okay. Insul omega has a lossy part, so they cannot be go to 0. They cannot be go to 0. It's about they have imaginary part. Okay. So the propagation length L should be as inverse proportional to the imaginary part of beta. Okay. So this is the reason plasmonic waveguide only travel very short distance because the beta is complex. Okay. Real part is the propagation part and the imaginary part is a lossy part. So when they propagation distance, they will decay. Okay. This is a real. This is a interesting picture for this surface plasma. The positive, negative, positive is the surface charge. It's a sign for surface charge. It's N dot D. Okay. So this is the wave connect. This is similar to called charge density wave. Physically called charge density wave. This is for charge distribution. Positive, negative. Because everyone knows the surface charge equal to N dot D. D is electrical flux. The electrical flux is a change of sign. Because it's a propagating wave, the positive and negative, like a sine and cosine, they change the sign. Physical picture. Okay. Then we go to this most important part, how to excite the surface plasma. Because surface plasma, I talk about is an eigenmode solution. Okay. You can see here, this airline. This is a dispersion relationship with surface plasma. Okay. At this point, they call resonance point. The kx goes to infinity. This is kx. Can go to infinity. Oh, okay. This picture not clear. I just draw this again. No matter, not clear. Okay, draw this. Okay. Something like this. This is k. This is omega. Okay, I use very simple model, Joule model. 1 plus
omega p squared over omega, right? This is a metal. I plus, I assume this air. This air. This is metal. Go to 0. So omega squared equal to omega p squared over 2, right? Right. No problem, right? So I just go to another step. You can say this is 2 minus omega p squared, omega squared equal to 0, then omega equal to omega p over 2. Okay, so this is just omega p over square over 2. This is omega p squared. Okay, this is omega p over square 2. Because this k goes to infinity, this is resonance. Okay, so this is the resonance. This is airline. This is airline. Okay, so everyone know why is omega over 2. This is a resonance condition. The Emerson dielectric plus Emerson metal go to 0. I just verify this omega p over square 2 for air. So if the dispersion relation is at the right hand side of airline, what's the feature? Is at the right hand side of this airline, what's the feature?
Plus 1.
Oh?
Plus 1.
Okay.
Plus 1.
Yeah. No. I mean, if the dispersion is at the right hand side of this airline, what's the feature of this mode? It's guided mode. Right? It's guided mode. This is important. So surface plasma also is a special guided mode. If the guided mode, what's the feature? Momentum mismatch. If you use plane wave, you cannot excite. Right? If you plane wave, you cannot excite. Because I just gave this another line. Okay. The K rho should be larger than K0. Right? K rho should be larger than K0. K rho is tangential wave number, or Kx should be larger than K0. The tangential wave number should be larger than the free space. And this is the guided mode. Because they must be trapped, right? That means the wave decay along air, right? Decay along air should be larger than this. Or else it cannot decay along air, right? If Kx is larger than K0, so Kz becomes an imaginary part, so they decay along air. So this is also a kind of a guided mode. You cannot excite with the plane wave. Plane wave, the maximum tangential wave number is K0. Okay, we cannot excite. This is a basic issue. So this is something I talked about this before. How to excite the guided mode. How to excite. I just give the first case. I can finish it this house. So surface plasma mode is a special guided mode because it's at right hand side of airline. Okay, at right hand side of airline. So for my course, you must know the wave physics well. Okay, what's the meaning of guided mode? What's the leaking mode? What's the surface state? Okay, okay, this is important. This is the leaking mode. This region leaking mode. This is propagating mode. This is the guided mode. Okay, this is guided mode. Region. So plane wave cannot excite the surface plasma. Okay, because it has momentum phase mismatch. Okay, the maximum K0, the maximum tangential wave number is K0. But for guided mode, the K rho or Kx should be larger than K0. So you cannot excite. You should provide the additional momentum to fill this gap. Okay. So first, how to excite it? Very simple with dipole. Right? I talked about many times with dipole. Because dipole, you can see this is a Sommerfeld identity, similar to the Welsh identity. The dipole is a solution for this scalar dipole. It's a green function. They can expand it as many plane waves. But the Kx and the Ky can go to the minus infinity, go to infinity. Okay. That means Kx and Ky can larger than K0. Can larger than K0. Because dipole, one dipole has an Evanescent wave component for the dipole source. So you pull the dipole very near from this
interface, you can excite the surface plasma. This is a picture. This is PEC interface. This is, you can see the PEC interface. This dipole. Nothing happened here. Okay, this is a dielectrical metal interface. You can see blue, red. You can see this is surface plasma, right? Because the charge, that means they change the sign. You can see they change the sign. When E field you change the sign, they have charge positive, negative. Because N dot D, right? N dot D equals to rho. When D is change the sign, you can see the blue is negative and the red is positive. Of this, you can have blue, red. This surface plasma nature. Okay, this surface plasma nature. Okay. Also, the decay, you can see they come out. Okay. This is can be inside. Use a diaphragm. Use dipole source. Okay, use dipole source. Your dipole source have evanescent wave spectrum. Because it's Kx and Ky can go to minus infinity, go to infinity. Okay. So how to excite guided mode? No matter how complex guided mode, you use dipole, you can excite it. But it's very close to interface. Okay. Because it has very broadband spectrum. This is a feature. So LED is a big issue because LED every point in the material is similar to dipole. So you inside many mode. Okay, inside many mode. It's very complicated. Okay. Then maybe I can talk about this a little bit. Okay. Another called Freedom coupling. Okay, Freedom coupling. They also have this way. Okay. You can see this is a metal film. Okay, the metal film is thin film, 20 nanometer. Okay, this is a prism. When the plane wave goes to prism, total reflection happens. But total reflection happens, the wave will become evanescent wave. They can excite the surface plasma, but they can excite surface plasma only at this side. Okay, this is interesting. They cannot use surface plasma at one top side. They only can excite surface plasma at the bottom side. Okay, this is interesting. Because this is a dispersion Y. Okay, this is a 2S surface plasma curve for metal prism interface and a metal air interface. Okay, it's because Kx equal to omega over C square root epsilon 1 epsilon 2 plus epsilon 1 plus epsilon 2. Okay, for metal epsilon 2 it does not change, but epsilon 1. This is a prism interface, this is air interface. So there's a different dispersion relation for the surface plasma, right? And a different dispersion relation. This is airline. This is airline for air, in air region, okay? I mean in this region, This is in prism region, Because there's a cross point here. In phase match can be achieved. The phase match can be achieved. Phase match can be achieved. So they excite at this metal air interface. Okay. So I mean it's the plane wave at this prism. The plane wave at the prism. Okay. Here. It's a match with this. Okay. This is easy to understand. Right? This is easy to understand. This part. Another setting we call auto fit configuration is something like this. You can see they move a little bit. They can excite. They have evanescent wave. Evanescent wave to excite this surface plasma. Okay. This is called auto. This is the most common one. We call it Craftsman. Another improvement is just use a two-layered Craftsman configuration. Okay. Between this metal film, they insert another layer. Okay. Use two layers. Then you can change the different angle. They can excite surface plasma at a different interface. They can excite that. Okay. Everything just see this curve. Okay. Just see this curve. Okay. Why the prism they has n is the n should be larger. For prism the n should be larger than the K0, right? Because it has the refraction index should be larger than 1. Right? So this is a tangential wave number can be larger than the K0. Okay, so they can excite the surface plasma. Because if the surface plasma is excited at this air and metal interface, the Kx should be larger than K0. Okay. So plane wave from air they cannot excite, right? Because the maximum is K0. But the plane wave at the prism is possible. Because prism the maximum is K0 multiplied N, right? It has a refraction index in here. So this can be excited. So this is a reason there's a cross point here. Okay. This is the reason. Okay. Someone use this structure to do the plasmonic sensing, or plasmonic or biosensing. Okay, why? Because the surface plasma is very sensitive. It's very sensitive to the dielectric environment. Okay, for example, from this structure. Okay, this is a prism. Maybe this is air. This is metal. Okay, if I put something above the metal, this plasmonic resonance frequency will shift. Okay, will shift. So it's very sensitive. Okay. You can see this is a picture. It's a picture. As a resonance, the reflection goes very small. The absorption becomes very large. It's a reflection at the plasmonic resonance. Okay, it's similar to couple mode. From here, the reflection wave. This direction reflection wave, it cancels out the reflection wave along another interface, cancel them out. So it has a very small reflection dip. If I put something above this metal, this angle will be shift. This angle will be shift, very sensitive. So people this will be commercialized. People put some called antibody and antigen. Okay, they put some antibody and here. Okay, they put some antibody below this metal. Okay, they put some antibody and shine the light to this. Oh, they find at a theta maybe 70 degrees they get the minimum, right? Now they put some maybe cancer cell onto cell. If we put some normal cell, nothing happens because antibody and antigen they cannot match them together. But if you put some cancer cell, when they match together, they do some chemical reaction. They change the environment. They change the environment above this metal. They can shift this angle and shift this angle. Okay. It's similar to that. So this last case, I mentioned about this in the next lecture again because this is important. This is a metal. This is dielectric. And I said, I change the permittivity of dielectric. I can shift this dispersion curve. Okay, it's very sensitive to this dielectric. Okay, if some reaction happen, they can shift this. Okay, I use some freedom. Some freedom inside this. I just survey the reflection coefficient. There's some dip. Okay, this is the first curve. And something happened, just shift narrow. Okay. Okay, if something happened, they change the permittivity of dielectric, they can shift to another. Very sensitive. Very sensitive. Okay, they use this method to do some biosensing. They put some antibody here. Or antigen, I can't remember. But they have some reaction, they see this reaction. Okay. If a normal cell can know this reaction. They have some cancer cell, they have some reaction, they change the permittivity. They shift this. Okay, this is commercialized. A very good application. Okay, so thanks for attending my lecture. Okay.